shape where they can rotate either to the right or to the left. Delta means to the right and lambda is to the left. Now, to help us understand the bonding in compounds, sometimes we use valence bond theory, and we learned about valence bond theory in Chem 1A. And for a linear shape, you have sp hybridization. So you're combining the two orbitals, the s and the p, to get this linear shape. Tetrahedral, there are four things. So there are four orbitals that are combined, so the s and 3 p orbitals, to make this tetrahedral shape. Square planar, you use dsp squared. So there are 1, 2, 3, 4 regions. So it's using the d is 1, the s is 1, and 2 p's. And for the octahedral, it's D2sp3. Now, I mentioned this right here in case this shows up on a standardized exam, but valence bond theory is not very useful or applicable to coordination chemistry and transition metals. It works very well for organic chemistry because it's very simple, and the carbon atoms with their s and p orbitals is very simple compared to the transition metals, which then also incorporate d and sometimes f orbitals. So valence bond theory is not a complex or sophisticated enough theory to completely explain transition metal complexes and their bonding. Now remember, bonding takes place when the filled atomic orbital on the ligand overlaps with an empty atomic orbital on the metal atom. So valence bond theory explains geometry as well, but it doesn't explain color and magnetic properties. So we have to have a different theory to better explain this. And this is where we've got to understand the shapes of the d orbitals. So just again a review, this is the dz squared. This is dx squared minus y squared. It lies on the x and the y orbitals. The dzx, the dyz, and the dxz. So here they give you the legend for the axes. So crystal field theory is a more sophisticated theory that better explains what's going on in the bonding and some of the magnetic and spectral properties of transition metal complexes. Crystal field theory says that the bonds form due to the attraction of the electrons on the ligand for the charge of the metal cation. So you've got an ionic interaction between the ligands and the metal. The electrons of the ligands repel electrons in the unhybridized d orbitals on the metal ion. So there are electrons in the d orbitals, and then there are electrons on the ligands. And when you bring these two together, like charges repel each other. So those repel each other. And the result is going to be a split in the energies of the d orbitals. So remember, when you did electron configuration, all the d orbitals were drawn on the same level because they were all considered degenerate. They all had the same energy value. But once you start putting ligands around the metal, those d orbitals are no longer degenerate. They're not all at the same energy level. They start to split to stabilize themselves, because when you start getting repulsions between the ligands and the metal orbital themselves, they'll split to relieve some of that repulsion. And the difference in energy on the complex, and the difference in energy in the orbitals when they split, depends on the complex and the kinds of ligands. And this is where we get into crystal field splitting energy and strong field splitting versus weak field splitting. So imagine the electrons, imagine the d orbitals on a metal atom, because without anything bound to it, so just a free metal ion, all of these d orbitals are completely degenerate. They're all at the same energy level. But now imagine an initial approach from a spherical shell around the metal ion, and it has this negative charge to it. So the electrostatic repulsion between the negative ligands and the d electron orbitals of the metal ion result in an increase in energy. So you have these ligands approaching, but they're in a way so that it's just uniform negative charge that kind of envelops those d orbitals and the orbitals on the metal ion. So initially you get this repulsion between the ligands, which are being represented by the blue, that negative charge, and the electrons in the d orbitals themselves. So this is why we have this increase in energy. Well, to relieve some of this, if there's not a lot of overlap with the d orbital and the ligand that's approaching it, those ligands go down in energy. But if you've got good overlap with the ligand and the d orbital, those ligands go up in energy. So orbitals oriented along the bonds increase in energy, and orbitals oriented between the bonds decrease in energy. But the overall energy is the same. So if we were to add up the energy between these five, where these three went down by some and these two went up, they have the same overall energy as these original five. But then you've also got to consider the adduct formation. So the ligand acting as a Lewis base, the metal acting as a Lewis acid, so you have this overall attraction due to the sharing of electron density, and this is why the complex being formed. So the electrostatic attraction results in a net decrease in energy compared to our initial free metal ion. And this is the driving force for complex formation, this lowering of energy compared to the initial free metal ion. So in an octahedral environment, the electrons split like this. You have the dz squared, the x squared minus y squared. Those go up in energy. So notice these go up in energy because if we look at how these are oriented, the d orbitals have these two lobes here, so you get a lot of overlap with these metals here. And then you have overlap with a donut with these ligands that are in the plane, this equatorial plane. So you have lots of overlap here. Lots of overlap means it goes up in energy. And in the dx squared minus y squared, remember these lobes lie on the xy axes. So the ligands are lying on these xy axes as well in the equatorial plane. So you have lots of overlap. So this goes up in energy as well. But for the dxy, the yz, and the xz, the orbitals lie in between the ligands. So you have the ligands here, and then you have the orbital lobe that comes in between them. So it just misses all of these. And so these are actually stabilized in energy. And these all just look the same. They're just rotated in kind of different positions. They're on the different parts of the x, y, and z axis. So you need to know how these orbitals split in an octahedral. There are 2 up and then 3 that are lower in energy. But for the other geometries, if you need them, we will give them to you on an exam. But you need to know for an octahedral complex how these ligands split. So we're going to talk about complex ion color. And this is the color of a titanium hexaaqua species. And this is the UV vis absorption. So in the visible region, it absorbs strongly at 498 nanometers. But you also have some absorption here. So it basically absorbs from about 450 to about 600 nanometers. But the color that's observed is the complementary color of the one that it's absorbed. So this is absorbing strongly in the so this is strongly absorbing in kind of like this green to yellow region. So the color that we see is the opposite. So this is why this has this kind of purplish reddish tint to it. So this is the color of the titanium complex. So it's absorbing strongly in this region, but it's reflecting all the rest of the color back, and we mainly see the opposite color. So hopefully you discussed this quite a bit in lab already. Now this is just to illustrate to you that the regions of color, these aren't evenly spread out. So notice that the yellow is kind of a little bit larger than some of the other color regions, like the green is very small gap. So this idea of using the color wheel and that the complementary color is reflected, this is a rough estimation of what we see. So the visible spectrum of this titanium complex consists of a single transition at around 500 nanometers. So if we look at how the d orbitals are split, remember we had 2 up high and 3 down low. The titanium complex, the titanium has a 3+ oxidation state. So there are 6 water molecules. Each water molecule is neutral. The oxidation state of titanium has to add up to the 3+. The titanium itself is 3+. So this corresponds to 1 electron in the d orbital if we did our electron configuration. And when this complex, when visible light is shown on this complex, it absorbs the energy, and that energy that it absorbs causes the electron to go from this ground state to this excited state. So the electron gets promoted. And this difference in separation corresponds to an amount of energy. So they call this the delta octahedral, so the amount of energy difference. So this is related to HV, so Planck's constant times the frequency. So the wave number difference, the energy related to this is 20,300 wave numbers. So the colors of complex ions are due to electronic transitions between the split sublevel orbitals. The wavelength of maximum absorbance can be used to determine the size of the energy gap between the split d sublevel orbitals. And the energy of the photon that causes the excitation from the ground state to the excited state is equal to h nu. And remember from Chem 1a, that's also equal to hc over lambda, where c is the speed of light, h is Planck's constant, and lambda is the wavelength. So this delta represents the separation in energy between the orbitals. So since we're mainly going to be looking at octahedral complexes, usually we'll say delta octahedral. So just kind of give you the difference and the color variability of some of these transition metal complexes. These are all cobalt 3+ solutions. So these all have the same oxidation state. They're all 3+. They all have 5 electrons in the d orbitals. And they all have octahedral geometries. The difference is the ligand attached to them. And then different ligands attached to them cause the different colors. So the A has cyanide ligands, B has the nitrite ligands, C is phenanthylene, D is ethylene diamine, E is amine, F is glycine, G is water, H is the oxalate, and I is the carbonate. And what's happening is, as we're creating what's called a spectrochemical series. And cyanide is a strong ligand, and it causes the d orbitals to be split by a lot. So if these are 5, so 1, 2, 3, 4, 5. So there's a bigger separation between these d orbitals for cyanide. And let's go to another complex. Let's do E, so the amine. The separation isn't quite as big with the amine. So you get a smaller separation. And this is, we get move in, and it's an orange color complex. But as we keep going to the right here, we get weaker and weaker ligands. So the separation becomes smaller and smaller. And so it takes less energy to excite an electron in the carbonate ion than it does in the cyanide. And if it takes less energy to excite it, this would be a longer wavelength of light. So if this appears green, we would expect it to be absorbing red light. And if it's absorbing blue light, we'd expect it to be absorbing orange light. And if it's absorbing purple, we expect it to be absorbing yellow. But eventually the separation gets to be so big that we move out of the visible region and it actually absorbs in the ultraviolet region. So this is why A appears colorless. It's because the energy gap is so large, it requires more energy, so it requires a shorter wavelength, and this actually gets us into the ultraviolet region of the spectrum. So pretty cool, huh? So the strength of the crystal field depends in part on the ligands. Strong field ligands include cyanide, nitrate, ethylene diamine, and amine. So this means that it has the ability to separate the d orbitals more. Whereas the weak field ligands, which are water, hydroxide, and the halogens, those aren't as able to separate the d orbitals as much as the strong field ligands. Now, if you needed the spectrochemical series, this would be given to you. You've probably already seen it on your cover sheet for your exams and quizzes. Let's talk a little bit more about ligand and crystal field strength. The strength of the crystal field depends in large part on the ligands. So this is where we're talking about the spectrochemical series. So it's like cyanide splits them more and iodide splits them the least. The crystal field strength also increases as the charge on the metal cation increases. So let's say we have an iron 3+ and an iron 2+. The iron 3+ has a larger charge, so you're going to see a bigger separation than you would for the iron 2+. It also depends on the type of the metal. Second and third row transition metals split more than the first row transition metals. And then the last criteria is the number of ligands. The more ligands that you have, the more the separation. This is why a tetrahedral complex only has 4 ligands. It has a smaller amount of splitting than the octahedral complexes that have 6 ligands. And so because the tetrahedral complexes aren't split as much because they only have 4 ligands, they always form high spin complexes. So what in the world do I mean by high spin complexes? Well, high spin or low spin will help us to determine the magnetic properties of transition metals. And the electron configuration of the metal ion with split d orbitals depends on the strength of the crystal field. The 4th and 5th electrons will go into higher energy gap, dx² minus y² and dz² if the field is weak and the energy gap is small, leading to unpaired electrons in a paramagnetic complex. The 4 through 6 electrons will pair the electrons in the dxy, dyz, and dxz if the field is strong and the energy gap is large. This leads to paired electrons in a diamagnetic complex. So this probably doesn't mean a hill of beans to you. So let's try to illustrate what they're talking about here. Here I've got an iron cyanide complex. Remember, the cyanide is a strong field ligand. It's going to split the d orbitals a lot. Whereas water is a weak field ligand, it's not going to split the orbitals as much, so the delta is small. Here, the delta is large. In the iron cyanide complex, each cyanide is a -1 ligand. So 6 times -1. And then overall charge is a 4-, so the iron has to be a 2+. And here for the iron, there are 6 water molecules, and each one of those is neutral. The overall charge is 2+, so the iron is going to be 2+. So the oxidation state in both of these are the same. And an iron 2+ corresponds to a D6 complex. So there are 6 electrons in the d orbitals. So when I'm doing that electron configuration for the iron, I'm writing the electron configuration, and then I remove the s electrons to get the 2+ oxidation state, and that gives me 6 electrons in the d orbital. So as I start filling in these 6 electrons, 1, 2, 3. So remember, I've got to use my rules when I did my electron configuration. I had to use the Aufbau principle, which is the building up principle. So you start at the lowest energy levels, and then you work your way up. Then there's Hund's rule. I have to fill them all half filled, and then I can pair them up. And then there's a Pauli exclusion principle. So no 2 electrons can have the same spin in the same orbital. So if these are all up, the next ones have to be down. So when I'm filling in these 6 electrons, I go 1, 2, 3, 4, 5, 6. And this results in a diamagnetic compound because all the electrons are completely paired. And this is what's termed a low spin complex. All the electrons are down low. But also, too, this spin number is 1/2 times the number of unpaired electrons. So the spin number is equal to 1/2 times the number of unpaired electrons. So this has a spin value of 0. But when we look at the aqua complex, and the gap is small between the d orbitals, I still fill in my first electrons 1, 2, 3. Now with my choice with my 4th electron, I can either come down here, down low, or move it up high. Rather than coming down low, because remember there's some pairing energy that's required. So if this one's spinning one direction, this one's spinning the opposite direction, they don't really want to get together. There's some repulsions associated with that. So the electron says, well, which one costs me less energy? To pair up and be crowded in this one orbital, or I can pay a little bit of extra money, put in a little extra energy, and get promoted to this energy level up here. So if the gap is small enough here, the 4th electron will go up in this higher energy level rather than being paired. So I go 1, 2, 3, 4, 5. But then my 6th electron, if I pair it up here, I've got to pay extra money to move in a higher level and to pair up. So I fill in my one down here. So this is where I get my paramagnetic compound. There are 4 unpaired electrons. And this is a high spin complex. So the spin value for this is 4 times 1/2. So the spin number is 2. So this has a high spin value. It's got a higher spin number than the low spin configuration. So notice both of these had 6 electrons. They were just paired differently. So here when I filled in my 4th electron, it cost too much money to promote it up to these higher energy levels. But if I paired it, it cost less energy. So it costs less energy to overcome the pairing energy. So if you got a big separation, you're going to have a low spin complex. If you have a smaller separation, you're going to have a high spin complex. But only electron configurations with a D4, 5, 6, or 7 can have low or high spin configurations. Because if you have 1, 2, or 3, you saw either way, it didn't look any different. But if I have 8, it won't look any different, and 9 or 10, it won't look any different. And you can prove this to yourself by drawing out the electron configurations for the high spin and low spin cases for the 1, 2, and 3, and the 8 and 9 to prove it to yourself. Now remember we said with crystal field theory, the ligands that are approaching and how they interact with the d orbitals change the way that the ligands split. This is how the ligands are split with a tetrahedral complex. The splitting is opposite of the octahedral. You've got the 3 up high and the 2 down low. Now again, if you were to need this for an exam, you'd be given this information. And if you have a square planar complex, the xz and the yz are the lowest in energy, then the dz squared, then the x squared, then the xy, and then the x squared minus y squared. So the x squared minus y squared is highest in energy because you have the most overlap with the ligands. Whereas the xz and the yz, remember those are above and below the plane, so those have the least overlap, so those are going to be the lowest in energy. And you're typically going to see square planar complexes with d8 metals. So they have 8 electrons in the d orbitals. And most of these complexes are going to be low spin complexes. So we just want to look at some of the applications of coordination compounds. Coordination chemistry is used to extract metals from ores. For example, silver and gold are extracted as cyanide complexes. Nickel, they actually use carbon monoxide to make nickel tetracarbonyl. So when they're extracting nickel from the ore, they actually produce nickel tetracarbonyl, but this is actually a very volatile and very deadly, one of the most deadly compounds known. Chelating ligands are used in treating heavy metal poisoning. For example, EDTA has a very high binding affinity for lead, and so if you were to be exposed to a heavy metal or have too much metal in your blood, you'd go to the hospital and they would give you a chelation therapy. So they're giving you a chelating ligand, and a chelating ligand binds more than once, so it has a higher binding affinity, so it's going to be more effective at extracting the excess metal from your body. Coordination compounds are also used for chemical analysis. So, for example, the qualitative analysis for metal ions, you'll be using this for the qual scheme. Also, in the field, drug agents will actually do tests for certain, like cocaine. They use a specific coordination compound, and if it reacts when it makes a certain color, they can verify that the compound is cocaine or other drugs. They're also used, coordination compounds are also used for coloring things because they're pretty colors, so they're used in inks and blueprints and cosmetics and paints. And there's also the field of bioinorganic chemistry. There are a lot of biomolecules that rely on coordination compounds, and many of these have porphyrin rings. So this is a porphyrin ring, so it's got 4 nitrogen donor atoms that fit around there so that iron or another metal ion can sit in that center. Cytochrome C is a good example of a coordination complex that's formed. A hemoglobin that has an iron in the center, so you have this heme group and the porphyrin ring around it, so you have iron porphyrin ring here and iron porphyrin ring here and in here. And then chlorophyll. Chlorophyll also uses a porphyrin ring, and this porphyrin ring has a magnesium at the center. And these act as antenna to harvest light as it brings in light energy in, it transfers energy so that you can undergo photosynthesis, the plant can undergo photosynthesis. There's also carbonic anhydrase. This is one of the fastest known enzymes. This is one of the fastest known enzymes. It helps catalyze the reaction between water and carbon dioxide. And it contains a tetrahedrally complex zinc. So it helps maintain the pH in your blood because CO2, remember the CO2 dissolved makes carbonic acid, so it has to help regulate the CO2 in your blood, to regulate the pH of your blood. It also helps regulate the pressure in your eye. So carbonic anhydrases are very important enzymes in biological systems. And coordination compounds are actually used in drugs and therapeutic agents. The most famous is cisplatin. This is a dichlorodimine complex, and it has to be in the cis form. And you can see the cisplatin linking and linking to the DNA, causing the bending of the DNA. So it's binding to the bases in the DNA and causing a kink in it. And this kink stops the replication of the DNA, which kills the cancer. So there are a lot of applications to coordination chemistry. I feel that we just don't have enough time to really go into the transition metal stuff, but hopefully the qual scheme kind of piques your interest, but it gives you a good appreciation, so that when you go on to your other classes, maybe your geology classes where you're trying to learn why some minerals are colored certain ways, or in your biological studies where you're looking at these different enzymes, these different metalloenzymes, you can better appreciate what the metal ion actually does.